Okay, so we can start the final session of the short talk. So the first talk will be given by Prangshu on uh, expected expectation in stochastic games with prefix independent objectives.
Hello everyone, am I audible? Okay, so this is sort of a continuation of the previous talk by Shivashish. In the previous talk, we looked at uh, a satisfaction version of the problem. We were given an objective, the window mean pair of objective, and our object, and we wanted to determine if player one can satisfy this objective with probability 1 or with some positive probability or with some arbitrary probability between 0 and 1. Okay, so now the next thing that we looked at was expectation. So we look at something called quantitative objectives, and the players will now try to maximize the value they can attain in expectation. So I'll just recap what we just saw. So stochastic games are infinite duration turn-based zero-sum games played on directed graphs without deadlocks. Okay, so I have drawn an example of a stochastic game here. We'll come back to it soon. Okay, and so in this part, we'll specifically look at quantitative objectives. As we saw before, that objectives measure how good a play is for the player. So we can look at an objective, let's say phi, as a function that maps to every play, to every infinite path in the graph, a rational number. Okay, so the higher the number, the better the play it is for player one. And since we are looking at zero-sum games, the objective of player two is the negative of phi. So it always adds up to 0. Okay, so let's look at some examples of quantitative objectives. So here I have 3 objectives. So one is the standard mean payoff objective. So what you do is you take the mean of the payoff seen in the first n steps, which is this term, and then take the limit as n goes to infinity. This is the standard mean payoff objective. Then this is the second one is a discounted sum objective, where the payoffs appearing later in the play are multiplied by a discount factor beta, and they contribute less to the total sum. And finally, here's phi WMPL. This is a quantitative objective defined in the following way. So it's the supremum value of lambda such that the play satisfies window mean payoff L with threshold lambda. So what happened in the previous talk was that we exclusively looked at lambda equal to 0, as in we wanted the window mean payoff to become non-negative after L steps. However, here we'll look at any arbitrary rational number lambda, and given a play pi, we want to find out this objective tells us what's the supremum value of lambda such that your play satisfies the window mean payoff with this threshold. And I'll just define what are prefix independent objectives. So these are objectives that are not affected by adding or removing finite prefixes from the play. So if you have an infinite path v0, v1, v2 and so on, if you remove v0, v1, the value of the objective remains the same. If you add few terms before, the value remains the same. So these are prefix independent objectives. Okay, and now, okay, so out of these 3 examples, the first and the third are prefix independent. However, the discount is not. So from now on, we'll only look at prefix independent objectives. Okay, and let's look at the problem statements that we studied. So we looked at the expected phi value problem and the synthesis problem. So the problems are as follows. So whenever you fix strategies of the players, say sigma 1 and sigma 2 of the players in a stochastic game, what you get is a distribution over plays. So if the players have decided that this is how they are going to play, then each time the you play the game, you may end up getting a different path, but you'll get a distribution over place, and this can be viewed as a Markov chain. And given a Markov chain, we can compute the expectation of this function phi, and that's what we denote here. So if your game starts from a vertex v, and here if the players follow the strategy sigma 1 and sigma 2, and your objective function is phi, then this is the expected value of the outcome. And the expected phi value problem is the following: is you're given a vertex v and a threshold lambda. You want to find out if for overall, if the supremum overall strategies of player 1 and in the infimum overall strategy of player 2, if the expected value of the outcome is at least lambda. Okay. And if once we compute such a lambda, we would also like to synthesize an optimal strategy for player 1. As in, we would like to find a strategy over here, sigma 1, that actually achieves this threshold lambda. So these are the problem statements. Are there any questions? Okay. Okay, so I'll point out some key observations that for prefix independent objectives. So in our graphs, we have 3 different kinds of vertices: player 1 vertices, player 2 vertices, and player 3 and probabilistic vertices. So this so for every player 1 vertex, for every circle vertex, what if you look at the expected phi value of that vertex, it is in fact equal to the maximum over of the expected values of its out neighbors. All right. This holds because it is a prefix independent objective. In particular, what the payoff of this edges does not matter. Similarly, if you have a player 2 vertex, an adversarial vertex, who is trying to minimize phi, then the expected value of v is the minimum over the expected values of the out neighbors. And finally, if you have a probabilistic vertex, then the expected value of that vertex v is the weighted sum of the expected values of the out neighbors, where the weights are the probabilities of these edges. Okay, so this property will be useful to us, and I'll just these, I don't know, your boxes are here. Okay, so this is our result. So what our main result is that we gave a reduction. We reduced the expectation problem to linearly many instances of the satisfaction problem, the almost sure satisfaction problem, which we saw in the last talk. So what we do is we start with this expectation problem. We ask if the expected value of phi is at least lambda, and we give a non-deterministic reduction to an instance of the almost sure satisfaction problem. We ask if player 1 can almost surely satisfy the objective that phi is simply greater than lambda. We'll see what these lambdas are. And okay, these are links. Okay, and our work builds on prior work by Tom and Florian Horn, and also Anne Condon. So in this paper, they looked at how you can solve satisfaction of Boolean objectives. Boolean objectives are where the range is 0 or 1. And they reduced it to an instance of almost sure satisfaction. We generalize it to quantitative objectives. And concepts from this paper were also useful in our proof. Okay. And I'll just state some assumptions that we had, that for complexity reasons, if you're given a game, we'll assume some bounds on the objectives. So we'll assume that the range is bounded and the denominator is bounded. That is, for every play that happens in a game, the value of the function is between some constant minus w and plus w, and there exists some value epsilon such that the expected value of every vertex can be written as p over q, and q is at most 1 by epsilon. So we are bounding the denominators of the values of the vertices. And our process is as follows: we guess the expected value of every vertex, and we'll show how you can verify them. And so for this we look at the concept of value classes. This was introduced by that paper by Krishnendu Chatterjee et al. So this is an example of a game. What we do is we guess a value of phi for every vertex, and we group each vertex together in what we call a value class. So we have grouped vertices that we guess have to have the same value in the same value class. So the purple denotes the value classes. So this, and we call them R1, R2, R3, R4, R5, and they have values. We also guess the values. So minus 10, minus 5, 0, plus 5, plus 10. So we are essentially guessing a partition and guessing also guessing a value for each partition. Okay, and there's something called a boundary vertex. So these are the vertices that allow you to exit the value class. So in particular, they are the a boundary vertex in a class is a probabilistic vertex which has some out edges out of the value class. So I have highlighted them in green here. So you see these are probabilistic vertex with some out edges, with some edges out of the value class. This is a probabilistic vertex, but it does not have any edge outside the value class, so it's not a boundary vertex. And player 1 and player 2 vertices are never boundary vertices. Okay. And finally, one last thing I would like to define is a restriction of games to value classes. So I've just removed the intermediate edges and I obtained 5 smaller games. And for every boundary vertex, I've added a self loop. That's all. So I'll call them GR1, GR2, and so on. Now I'll finally come to our algorithm to verify our guess. So I'll give 4 conditions that we claim suffice to verify the guesses. So first of all, the first condition is that each restricted graph is in fact a game. By that I mean it does not have deadlocks. Okay, and we also want the observation that I pointed out before to hold for every vertex. So these are 2 things that we need to verify. In addition to this, as I mentioned before, we check almost sure satisfaction in each of these smaller subgames. So we want to check in each subgame GRI if player 1 can win an objective. This is, now you can look at this as a Boolean objective. If player 1 can satisfy this almost surely. Okay, and we also check if player 2 can satisfy this objective almost surely. So what is this objective saying? This objective is saying that player 1 can achieve, if we guess the value of the value class to be Ri, player 1 can achieve values slightly less than that. Epsilon is a small quantity, slightly less than Ri, with probability 1 in fact, by staying inside the value class. I'll give an overview of the proof for this, as in why these 4 conditions, if these hold, why does it imply that our reduction is correct, our guess is correct. Okay, so I'll just briefly state the steps. So both players have a strategy to ensure almost surely that a token eventually enters a value class from which it never exits. So you have multiple value classes. It could be the case that the token keeps moving between value classes forever. Okay. But we claim that both players, either of them can individually ensure that the token eventually reaches a value class from which it never exits. And by prefix independence, the value of the play does not depend on the initial finite prefix, so it only depends on the value class it ends up in. And from the 3rd and 4th conditions, we have that player 1 can ensure at least Ri minus epsilon, player 2 can ensure at most Ri plus epsilon, and because of the bound on the denominator, we have that the value is exactly Ri. And finally, we see how it applies to the window mean pair of objectives that we saw. And this is our theorem that we obtained from the reduction. So we say that if L is in unary, then the expectation problem for WMP is in fact in UP intersection co-UP. This is the unambiguous non-deterministic polynomial class UP. And I'll just briefly state the proofs. So to show that something is in UP intersection co-UP, we just need to show that there's a short certificate. And this follows from this observation that every value class, that the value of every vertex for this objective can be written as a mean payoff of path of at most length L. And the fact that this is a unique value follows from Martin's result on determinacy. And finally, from this previous paper on satisfaction, we have an efficient method for the almost sure satisfaction. So this follows. And yeah, to conclude, we gave a non-deterministic reduction and we made use of value classes. We extended them to quantitative objectives, and we showed for these two objectives that they are in UP intersection co-UP, and our method also gives up an alternate proof that mean payoff is in UP intersection co-UP. And future work is that we would like an implementable algorithm for maybe using value iteration perhaps. And this is what Shibashish mentioned, that beyond worst case, this is another problem, interesting problem to look at. Thank you.
Let's thank the speaker, and maybe we can take the questions offline because we're running a bit late and it's the last session. So thanks. Okay, so the second talk will be given by Jakub about ideas to solve games faster.
Sorry? Is it on? Yeah, okay. So, hello, I'm Jakub, and I will tell you something about some ideas about solving games faster. It's work with Krishnendu Chatterjee, right? His name you heard quite a lot. With Raimundo that sits there, with Ali Asadi and Tobias Meckendorfer. So it's I will just like these main ideas of two papers. One is leaks this year, and then the previous one is Soda last year. So it's very high level ideas. What do we want to do, right? And people before me defined what are the turn-based stochastic games, right? So I repeat it very briefly. So that we have a graph. Vertices are partitioned to the three or states are partitioned into three groups, and this is the random one, maximizer one, and minimizer one. And I want to point out that if you use maximizer with the triangle pointing up, then it's obvious that it's someone who wants to maximize the value. No. Yeah, and then there are some transitions, right? So and then there is a token that runs around the graph, and then if it lands in the random vertex, then it goes somewhere randomly along the edge, right? So here it's 50-50, and here the minimizer chooses whether to go left or right. Right, and then we can have some different objectives. The classical one, the simplest one is the reachability, right? So if we have one state that is one that maximizer wants to reach, and the other one is 0 that the minimizer wants to reach, or minimizer also wants to stay in the graph forever. Right, so that's the setting, and we will also work in a similar setting, which is discounted sum. So some edges have some reward. So some of them might be 0. This might be -1, right? This edge is 1, and then we will have some path, and note that now there is missing missing the randomized vertex, right? So it would be for just deterministic games, and then after we get the path, we will get the rewards, and our payoff will be the discounted sum of the payoffs. And then again, maximizer wants to maximize the sum, and minimizer wants to minimize. So what do we know about this games? And this is that pure memoryless strategies are good enough. That means that if we are in some vertex and we have some decision to make, we can just make it forever. It doesn't matter on history, how we got there, but there is always one choice. And then we also don't need to randomize, meaning that there can be just one choice always, right? So it's not like a 50-50 going left or right. And this actually means that it's in NP intersection quantity. That means that there can be some nice and efficient algorithm, right? How do we solve these games? Of course, in previous talks we heard something how to solve them smartly and how to solve them for maybe a little bit complicated objectives. But in general, it would be two ways, either strategy iteration or value iteration. In strategy iteration, we somehow go through possibly all strategies, and then we will try a strategy, find a counter strategy. So usually if we fix one strategy, then it's easy to solve the game in polynomial time. We'll fix the strategy, find a counter strategy, and then this gives us how we can improve our fixed strategy such that we will eventually converge to something better. And value iteration, this is the idea is to say in every vertex we will keep the number how much we can guarantee that the maximizer can achieve, meaning what payoff he can achieve, or what the reachability. So since our approach is tied closely to the value iteration, the value iteration works like this. We will start with the value 0 in every vertex, except this vertex has value 1, right? And this has value 0. These do not change because these are the targets. And then every vertex looks at the at all the successors and update itself, right? So if there is a random vertex, then he chooses weighted average from the successors, right? So this one sees 1 and 0, so it will update to 1/2. This is the minimizer. He chooses minimum of the things he sees, so he chooses minimum between 1 and 0. So we see that we get 1 from here, 1/2 here in the first step, and then we get again. Right now, maximizer sees 1/3 and 1/2, so he updates himself to 1. No, sorry, 1/2 obviously. And then eventually, if we run it long enough, then we will get to something spoiled. So we can run very long until we get to the fixed point, and this is maybe not very efficient, right? So maybe we can go and increase the vertex a little bit step by step. So maybe there might be an idea to guess what is the exact value of this vertex, right? And we can say, for instance, let's guess that it's 1/2, right? We'll say it's 1/2, and then we will solve the rest of the game as this vertex value is 1/2, right? And then after we solve the game, and we remove this vertex. So like, if the token jumps to this vertex, the payoff is exactly right. And after we get to the solution, and now it doesn't matter how we get to the solution. We just go to the solution where we have value in every vertex. That is the the maximum maximum out of all successors for the maximum, right? Minimum of all the successors for minimizer, and average of all successors for the random vertex. We will look what if we updated this guy, the one. So before it was a maximizer vertex, right? It was a maximizer. So he chooses maximum of these two vertices. And know that at least one of them is above 1/2, right? So that means that if we now run the value iteration, this value would increase, and all the others so far were exactly equal to the update. That means that the values inside can only inside the game can only increase. Can only increase. That means that this value was under approximation of the value. So now we can run a binary search to get to the correct value. Now, yet the idea doesn't give us anything, right? The binary search needs to have a lot of iterations, but we can notice something here. If the token wants to go from up to here, it cannot, right? So if we guess this guy, and then recursively we guess this guy, then we split the graph into two parts, and these parts do not influence each other. So that means we can solve one part of the graph and the other part of the graph. So we by the guess we change the structure. So this gives us the first theorem. So we have a stochastic game with bounded tree, and we can do it in quasi-polynomial time if the tree is bounded. And now for the other idea, that we have a discounted sum, right? So again, we have some path that was created with some payoffs, and then we have a discount lambda this time, not beta. And we know that this game can be solved in time that is some polynomial, and then 1 minus the lambda, right? So if the lambda, if the time horizon is very short, like lambda is 1/2, then we can solve it very quickly. But if it's exponentially close to 1, then it's half, right? And then it increases. The closer it is, the harder to 1, the harder. So if we have such a game, then we have game, deterministic game. Then the strategies form the lasso shaped play, right? That means that if a maximizer in A chooses right, then it goes first through some path, and then it's a cycle, right? Remember, every vertex deterministically can choose the optimal solution, optimal successor. So it will be path and cycle, right? And now we can actually rewrite this discounted sum as a this is the path contribution, and then there is a contribution that comes from the cycle. And since it's repeated always, then it's then we can sum it up, right? And then we just sum up the geometric series. So this is some polynomial at most of the size at most n, or of the degree at most n, and this one is also some polynomial. And now we don't try to find like the best value. What we want to try is to look how the different strategies, how they create different polynomials, and how these polynomials interact with each other. Which one is the best? And sorry, this is like 30 seconds, right? So what we find out is that the closer the polynomials can cross each other quite often, right? Depends on a degree and stuff like that. But if the polynomials have some common root in when lambda is 1, then they cannot cross too short before that. So there needs to be at least some gap, right? So if we have some roots of the polynomials, these are the roots of all polynomials that have roots around 1, right? So then there is some small gap. So the idea is to actually solve the game for some lambda that is a little bit away from 1, meaning that it's faster. And then we show that this result actually also works for all the lambdas that are higher, up to, right? So this gives us the solution, and this is n to the square root of n, and w is the absolute weight. So we want to have the weights to be in unit. And these are the papers. Thank you for your attention.
Any questions? Just one short question, maybe. So can you just say what W was? Is it given in binary or unary?
Yeah. So if we have W in unary, that means so
it's the weight of edge.
yeah. So this is the reward that we get if we take some position.
Okay.
All right.
Thank you. Hi, Shayan. So, yeah, thanks for joining. So, can you share your screen and start your camera? Yeah, also, you have to unmute yourself.
Yes. So am I audible?
Yes. Yeah. Okay, so the last talk of the workshop will be given by Shayan about bio-objective lexicography optimization in MDPs. Thanks.
Yeah. So hi everyone. I really wanted to be present there in person, but as luck would have it, I could not go, so I had to stay back. So I am in Brussels, and I will be giving you this talk online.
Shayan,
So yeah,
the screen.
is it not visible?
No, this. Can you share it again?
So so you can see the slides now,
Yes.
but you cannot see when I. Okay, wait. You cannot see anymore?
No.
Okay. Sorry about that.
So, people are suggesting you do a full screen share.
Yeah. So maybe you can see it now. Yeah, can you see it?
Yes.
But is there some, yeah, can you see the full thing, or there is some place that are being blocked? No, okay.
You can start.
Yeah, okay. So hi everyone. So today I will talk about, as Shogata said, by objective lexicographic optimization in Markov decision processes with related objectives. So it's a long name, and I will try to explain as much as I can in the next 10 minutes. So this is based on a work that we published in ATVA last year, and it is a joint work with Damia, Debraj, Anirban, Guillermo, and Jean-François. of whom probably Damia and Anirban are there in the audience among you. So yeah, and so one good thing about being online is that so probably after a long day, you all are very tired. So if you all want to go to sleep, you can. I will not be able to see you because I only see the screen. And I will just assume you all are going to pay a lot of attention to what I'm going to say. Okay, but I will not go into any technicalities. It will be a very high level talk. So, okay. So let's try to play a game. So here we have a maze, as we always have. And then in this cell, you have a robot. And in this cell is where you want the robot to go. Now, between cells, you have some pathways. So once the robot is in a cell, you can ask it to go to another cell, right? And then the objective is to find a strategy for the robot that will give the maximum probability to reach the target. Now you will ask me, where is the probability coming into the picture? So let me tell you that. So suppose this is where the robot is and you ask the robot to go to the right cell, right? So you ask the robot to move right. Then with half probability, the robot indeed move right. But with 1/4 probability, it slips. So it can either go up or it can either go down, right? So this could be any arbitrary probability distribution, but for this demonstration, let's just assume that this distribution is like this, right? Okay. So now we have this objective in mind. And if I ask you, how would you ask the robot to go from this situation? You would probably just say the robot should move up, right? But suppose I considered this strategy where I ask the robot to move down, right? And from the remaining cells, it moves according to the arrows. Okay, so from here you ask it to move right, from here you go right, this, and if it is here at some point, then it can go there, right? Now, then as probability would have it, you would see that the probability to reach the goal state from this initial state is still 1, right? And so this is still a valid strategy for this objective that we consider. But quite clearly, we don't really want this strategy to be the output of our algorithm, right? So what can we do to get rid of this strategy? So ideally, we add another optimization, another objective on top of it, which will hopefully remove this red strategy as one of the valid strategies. So what is this second objective? So for this, we can consider that, okay, we first want to maximize the probability to reach the target, but once that is achieved, maybe we want to also reach the target as soon as we can, right? And with this second objective in the picture, you clearly see that from here, now it is better for the robot to go up and then go right, right? Because it will still maximize the probability and it will, of course, reach the target sooner than this red strategy. Right. So with this strategy vanishes. And this brings me to the first part of the title. So this is why we consider bi-objective lexicographic optimization. So we have two objectives and we have a lexicographic priority over the objectives. We first want to maximize the probability and then we want to minimize the expected number of steps to reach there. Right. So the maze that I showed you was just for demonstration purposes and it's too small a maze. So this is what the actual maze where we do our experiments on. And this is a standard benchmark. So it's called frozen lake. So here, this is a lake, which is frozen. And you have some rocks and you have a robot. You have some holes where once the robot goes, it cannot come out anymore. And then you have a goal state, right? And because this field is slippery, the robot has some probability to always slip to an adjacent cell than the cell that you intended it to go. Right. So on this, when we apply our algorithm, so this column is the number of steps that the strategies that we output take. And these are the numbers that if you ask Storm, which is a model checking tool, if you just ask it to give you a strategy that would maximize the probability to reach the target, according to those strategies, you would have taken these many steps to reach the target. So you see there's a clear advantage of being able to consider two objectives one after the other. So good. Now let's So I say the second objective is to reach the target as soon as we can, but this is not really formal, right? So let's make it a bit formal. So we say the second objective is to actually minimize the conditional expected number of steps to reach the target, conditioned on the fact that you actually reach the target, right? So now how do we solve this? So let's get to the algorithm. So we first start from the maze, from the frozen lake grid, and we convert it into an MDP. So you have already seen MDPs during previous talks, but I will still just say what it is. So basically here we have some states which are marked in circles. And from a state, once you take an action, now instead of deterministically going to one state, you have a distribution over states, right? So from here, you have some probability to go here and some probability to go here. Similarly, here you have some probability to go back, some probability to go there, some probability to go there, and so on. Now, this green state is the state, the goal state that you want to reach. And once we have modeled this, we completely forget about the actual game, and we try to analyze this MDP ourselves, right? So what do we do? So suppose this is the set of all strategies of the MDP. Okay? So this is the whole search space from where we want to pick one strategy for our purpose. Now, the first step that we do is we prune the MDP. So how do we prune it? So basically, from every state, we figure out which of the outgoing actions are part of some optimal strategy for objective one, right? So we remove this action because this action was not part of any optimal strategy. So if you basically play this action from this state, you are doomed. You will never be able to satisfy this you will never be able to maximize the probability anymore. So you figure out, so this is a very local property, right? From every state, you see the outgoing actions, and then you do this computation and you remove some of the action. Now, then you can see it may happen that we also remove some of the states, and there was some probability going into that state. So in order to keep this new pruned thing an MDP, we redistribute this probability among these two so that the whole sum remains 1 and so on, right? So once we do this pruning, we get a smaller MDP that contains all the strategies that maximize the probability to reach the target, but it also contains some strategies that does not maximize. Okay, so this may be a little unintuitive what I'm saying. So let me show you an example. So let's consider this example. Okay, this is an MDP, but it doesn't really look like it, but let's say it's a completely deterministic thing. So from this state, if you read an A with 1 probability, you just stay here. And if you read a B with 1 probability, you go there. Okay? This is an MDP. Now, if we try to maximize the probability to reach this green state, we see that there is this strategy of taking first an A and then a B, right? Which will still be an optimal strategy for reachability. So if you prune it, essentially nothing will be removed and you will have the same MDP as it was. But here you also have the positional strategy of only playing A forever, right? But that strategy does not maximize the probability to reach this state. So these are some spurious strategies that we don't really want to consider for the second objective. So that's why we kind of need a second objective, which is tailored towards the first objective, so that when you optimize the second objective in the pruned MDP, you will get rid of such spurious strategies. Okay, so that's why we say related objectives, and you cannot really consider any arbitrary objective as your second objective. Right. So now that that is done, so what is our second step? The second step is just to find strategies that minimize the expected number of steps to the target, right? And here I cross out this conditional because you don't need to consider the conditional expected number in the pruned MDP anymore, thanks to this result, which essentially says that, so in the pruned MDP, the expected number of steps to reach the target is actually the conditional expected number of steps to reach the target in the original MDP, right? Okay, so with that in mind, now that we have the pruned MDP, we just find set of optimal strategies for the second objective, okay, and the unconditional objective. And we know that both these objectives can be done with positional strategies. So you can just use any off-the-shelf model checkers that will give you the strategies for this. Right. So yeah, so that's all essentially that I wanted to say. So our main contribution is a two-step algorithm, which first prunes an MDP and then solves a second objective on the pruned MDP. And we prove that this algorithm works when the first objective is reachability. So basically maximizing the probability to reach a state. And the second objective is the expected number of steps. And this is what I explained so far, but it also works if your first objective is safety. Now, when you consider the first objective to be safety, essentially, you now want to find a strategy that will avoid visiting some states in the grid, right? And with this objective in mind, when we prune our MDP in the first step, actually, we don't have any spurious strategies anymore, unlike the case for reachability. So when the first objective is safety, you can take your second objective to be anything and it will just work, right? So yeah, and we are trying to find more pairs of objectives where this algorithm will work. If you want to see the proofs and more details about this algorithm and everything, you can find it in this paper. And if you have any questions, I would be very happy to answer them. So maybe I'll stop the share and I will.
Thanks. Any questions?
Hello, fine. So yeah, I have a couple of questions. So one is that so in this two-step process, um, I first step, so you are doing the planning. That time itself, is it possible that like for the reachability objective, for example, like can you do some kind of a backward?
Sorry, I cannot really hear properly. Can you repeat?
Okay. Are you able to hear me now?
Yes, perfect. Yes.
Sorry. So, so I was asking, like, you were talking about this two-step process. So, for example, this reachability followed by this expected number of steps. But
Yeah.
computing these the strategies for the reachability objective, the optimal strategies for the reachability objective, can you also at that time itself, can you also do some kind of a backward analysis from the reachable states and try to figure out what is optimal in terms of the number of expected steps? I mean, rather than doing it in two phases, like, can you combine the two?
Yes, so I think that's a good suggestion. So perhaps you can do that, but so we just use these two objectives as we want to use just off-the-shelf tools. So when we just ask the tool to give us a strategy to optimize the probability, it just gives us that. And we don't really did not at least want in this work to analyze the intermediate steps. And so the thing that you propose would require us to go a bit more low level into the first computation. But then, yes, I guess you can do that. But I don't know how it will be compared to just using off-the-shelf tools for the two objectives separately. But it is indeed a valid thing to try, I think.
Okay. And the second question is that, like, so you are using, for example, Storm for both the objectives, one after another. So you run Storm first, and then it gives you the set of all optimal strategies with respect to reachability. And then again, you are running Storm or another model checker for the expected number of steps, which gives.
Yeah. So basically, we don't compute all the strategies for the first objective. Instead, what we see that, so you can compute some sort of a value of a state, and you see if taking an action kind of reduces the value, which would mean that if you take that action, then you cannot optimize the probability. And so then you remove that action from the MDP. And for the second objective, we just ask Storm to give us one strategy that will satisfy the second objective without the condition in the reduced MDP. And then it just gives us some strategy that we also output. And yeah.
Okay. And for the second pair, like the safety and the mean payoff,
Yeah.
the safety you prune, like you kind of wrote the code yourself, like to prune the prune out the actions which are unsafe, or is it also like you are getting that using Storm, like the set of all safe actions, like from every state, like how?
Yeah, so we actually did not implement the safety case. So we only implemented the reachability where we were pruning it ourselves. So we were using Storm to compute the values of the nodes, but then we were just pruning the things ourselves to get the smaller MDP.
Okay, and how does it scale? Like the whole thing, how large MDPs can you use? Like 1 million states or more? How?
So I won't be able to answer this. So I think we only tried it on these layouts, and I don't remember how large the MDPs were for these. Sorry, yeah. But
Okay.
maybe you can find my other co-authors and they may be able to say you better. But yeah, I don't know how are the sizes of these MDPs.
Okay, thanks.
Yeah, thanks.
So the speaker,
Yeah.
yeah, so to conclude, so the workshop is over.
Okay, so I will. Yeah.
Thank the other organizers. So Suman is here, and also Tejaswini, who could not join us. And I would also like to thank Srivatsan and Akshay, who encouraged us to organize this workshop. So thanks everyone, and thanks to all the speakers, and thanks.